Imagine you have a massive, completely unsorted list of data. Searching through it piece by piece from beginning to end? Yeah, that's incredibly slow and tedious. But what if there was a way to organize that data so perfectly that you could find exactly what you're looking for in a fraction of the time? Well, today we're unlocking a brilliant structural solution that does exactly that. In this explainer, we're demystifying binary search trees.
Okay, let's dive into this. Our roadmap for today covers 5 key areas. First, the binary search tree definition. Second, building and sketching. Third, searching and inserting. Fourth, deletion and traversal. And finally, performance and pitfalls. Let's get started.
Section 1. The binary search tree. The fundamental rule of data shape. To truly get a handle on this incredibly powerful data structure, you really don't need to memorize complex code right out of the gate. You just need to grasp one absolute unbreakable rule. A binary search tree, or BSC for short, is a tree-based data structure where each node stores exactly one value. And here is the golden rule. For every single node, any smaller values absolutely must go to its left subtree, and any larger values must go to its right subtree. I literally cannot emphasize this enough. This single rule has to be true for every single subtree in the entire structure, not just the very top root node.
Let's think about this concept in action. Say we have a root value of 8. Following our rule, the entire left branch extending down from that root can only contain numbers smaller than 8, like 3, 1, and 6. And the entire right branch? Only numbers larger, like 10 and 14. Now, zoom in one level down to that 3. Even here, the rule applies perfectly. Its left child is a smaller 1, and its right child is a larger 6. It's this elegant, recursive pattern that holds true no matter where you look in the tree.
Moving right along to Section 2. Building and sketching trees. Turning data into a pathway.
Now that we know the abstract rule, I challenge you to use it to actively build a tree from scratch. Building one is honestly like laying down a physical pathway where you make a simple binary choice at every single fork in the road. Step 1, start with the very first value in your dataset and make it the root node. Step 2, take your next value and compare it to that current node. Step 3, move to the left if the new value is smaller, or to the right if it's larger. And finally, step 4, just keep moving down until you hit an empty position and plant your new node right there.
Now, what's really interesting is tracing how specific values fall perfectly into place. Say we have a sequence starting with 40. That 40 becomes our root. Next is 20, smaller than 40, so it goes left. Then 60, larger, so it goes right. When a 10 comes along, we compare it to 40, go left to the 20, compare it again, and go left again to place it. Just by following those basic steps, a random sequence naturally branches out into a perfectly structured tree.
Quick heads up, before we move on to using the tree, I have to give you a massive warning, especially if you're tackling a computer science exam anytime soon. Never, ever sort the original list before sketching your tree. Always insert the values in the exact order they are given to you. If you think, oh, I'll just put these in numerical order first to make it easier, you will actually draw a completely different, entirely incorrect tree. The final shape depends 100% on insertion order.
Section 3. Searching and inserting data. The fork in the road.
This is the real action sequence of our explainer. We've meticulously built our tree, now we put it to work. Searching a BST uses the exact same logic as building it. Step 1, start at the top root. Step 2, compare your target value with the current node. Step 3, follow only one branch, either left or right. And Step 4, you either arrive at your target or you hit an empty space, which means the value simply isn't in the tree. The beauty of this design? At each step, you only follow one branch. With every single move, you are essentially eliminating half of the remaining search space.
Let's mentally walk down the pathway together to find the value 55. We start at a root, let's say it's 45. 55 is greater than 45, so we move to the right branch. Now we hit a 65. 55 is smaller than 65, so we take the left fork. And boom, there it is, we arrive at 55. In just 2 simple comparisons, we completely bypassed the entire left side of the tree. That right there proves just how elegant and fast this search algorithm really is, compared to checking every single number in a list.
And what happens if we want to add new data to an existing tree? Let's say we insert the value 26. We start at a root of 30, go left to 20, go right to 25, and then right again into the empty space. Notice that the new value, 26, is simply added as a leaf at the very bottom. You don't have to break apart or rearrange the entire existing tree structure to accommodate new data. You just follow the path until you find an empty spot and drop it right in.
Section 4. Deletion and tree traversal. Maintaining the rule and revealing the magic. Get ready, because this next part is essentially the boss battle of the topic. Removing nodes threatens to break our perfect left and right rule, but don't worry, I'll guide you through this. There are exactly 3 cases of deletion you need to know. Case 1 is a breeze. Deleting a leaf, a node at the bottom with no children. You just remove it directly. Case 2 is deleting a node with 1 child. Here, you just link the deleted node's parent directly to its child, effectively bridging the gap. Case 3 is the tricky one, deleting a node with 2 children. You can't just delete it or you'll leave a bunch of orphaned branches. Instead, you replace it with its in-order successor, which is just a fancy way of saying the very next largest value in the tree.
Let's see how these 3 cases play out. Removing a leaf like 12? Easy, it just vanishes. But what if we want to delete a 30, which has a single child, 35? We literally just bypass the 30 and link the parent directly down to the 35. Now, the tough one. Say we delete a 50, which has 2 full branches below it. We look at its right subtree, find the absolute smallest value there, say it's 60, and we slide that 60 up to take 50's place. Doing that perfectly preserves the BST rule without breaking any branches.
Okay, so we know how to alter the tree, but how do we read the whole thing at once? We traverse it. Think of this as your ultimate cheat sheet. Depending on how we literally walk through the tree, we achieve totally different goals. In-order traversal visits the left branch, then the root, then the right. Pre-order hits the root first, then left, then right, which is perfect for making an exact copy of the structure. Post-order goes left, right, and hits the root last, and that's what you'd use if you need to systematically delete or evaluate entire subtrees.
If you're tracing an in-order traversal on a sample tree, you'd go all the way down the leftmost branch to find the smallest number, say a 1, then up to its root, a 3, then right to a 6, then way back up to the main root, an 8, and so on. A quick tip, you absolutely must write out the nodes in this exact mathematical visiting order. Do not simply list the levels of the tree reading top to bottom, left to right like a book. You have to follow the specific traversal pattern.
And here is the absolute magic trick of the binary search tree. In-order traversal of a BST gives values in sorted order. Period. Think about how crazy cool that is. Despite its branching, complex, and sometimes chaotic-looking shape, the data was perfectly sorted all along. Just by following that simple left root right pattern, a perfectly sorted sequential list emerges straight from the branches.
Section 5. Performance and pitfalls. Why tree shape changes everything. Let's explore the limits of this structure and look at what happens when things don't go perfectly to plan. So, the crucial point here is the final shape of the tree. There's a drastic contrast between a wonderfully balanced, shallow tree where every fork gives you a real choice, successfully halving your search time, and what we call a skewed tree. A skewed tree is essentially just a straight diagonal line of nodes. This physical shape completely dictates your real-world performance. If your values happen to be inserted in a mixed, balanced way, you get blazing fast O of log n time. But if you insert values in an unlucky order, for instance, if you inserted data that was already sorted sequentially like 1, then 2, then 3, then 4, you get that skewed tree. At that point, you lose all your efficiency. The tree degrades into nothing more than a basic linked list. Searching it takes slow O of n time, which is literally no better than just scanning a list item by item.
To wrap up our technical deep dive, let's summarize some common pitfalls. These are incredibly high-value takeaways if you're facing an upcoming assessment. 1. Sorting values before you draw. We said it before, but seriously, do not do it. 2. Forgetting that the left is smaller, right is larger rule applies to every single subtree. 3. Writing out a tree level by level instead of doing a proper traversal walk. And 4. Messing up that 2-child node deletion by not using the in-order successor. Avoid these and you're golden.
As we finish up this explainer, I want to leave you with a provocative thought to chew on. Why does in-order traversal give sorted output? Challenge yourself to reflect on the elegant mathematical logic we've explored today. Think about how that single, incredibly simple rule about left and right creates perfect, hidden order out of a pile of raw, unsorted data. Keep wondering, keep exploring, and I'll catch you in the next explainer.